Good morning to one and all present here. I am R.Maheshwari, Assistant Professor of Chemistry, A.D.M.COLLEGE for Women, Autonomous, Nagapattinam. Now, today we are going to discuss about the topic is catalytic hydrogenation by using Wilkinson catalyst and reduction reactions. Table of contents. First one, Wilkinson catalyst, and second one, sodium borohydride. It's a reducing agent, and lithium aluminum hydride. What is a Wilkinson catalyst? A homogeneous hydrogenation catalyst. Tris-triphenyl phosphine rhodium chloride. It's a IUPAC name of chloro-tris-triphenyl phosphine rhodium 1. These are the structures of Wilkinson catalyst. Shape and oxidation state of Wilkinson catalyst. It's a square planar structure. It's a 16 electron complex. It's the oxidation state of rhodium +1. Application. It's used in the selective hydrogenation of alkenes and alkynes. Alkenes, it's catalyzed high temperature and atmospheric pressure. Finally, we get the product of alkane without affecting the functional groups like carbonyl, cyanide group, nitro group, aryl group and ester group, etc. Contents. Properties of Wilkinson catalyst and preparation of Wilkinson catalyst. Then third one, mechanism of catalysis for the hydrogenation of alkenes, and last one, applications of Wilkinson catalyst. First one, physical properties. It's a molar mass of Wilkinson catalyst is 9 to 5.22 gram per mole. It's a melting point 5182 to 523 Kelvin. It's insoluble in water, but it is soluble in many hydrocarbon based solvents such as benzene and tetrahydrofuran. Then chemical properties. Wilkinson catalyst has a square planar coordination geometry. It reacts with carbon monoxide to yield bis-triphenyl phosphine carbonyl rhodium chloride. This coordination compounds undergoes dimerization. When stirred into a solution of benzene, the chemical composition of dimer can be expressed as bis-triphenyl phosphine rhodium chloride. Preparation of Wilkinson catalyst. Wilkinson catalyst can be prepared by reacting hydrated rhodium 3 chloride with the excess of triphenyl phosphine in the presence of ethanol. The product of Wilkinson catalyst is formed. These are the preparation of Wilkinson catalyst. 4 mole of triphenyl phosphine, it reacts with hydrated rhodium chloride. Finally, we get the product of Wilkinson catalyst. Next one, catalytic hydrogenation by using Wilkinson catalyst. Catalytic hydrogenation of double bond to form alkane by using high temperature and pressure. Alkene is catalytic hydrogenation at high temperature and pressure. We get the product of alkane is formed. The pressure involved in the complex tris-triphenyl phosphine rhodium chloride is also known as Wilkinson catalyst. Wilkinson catalyst can be dissociated into bis-triphenyl phosphine rhodium chloride and triphenyl phosphine is formed at the rate of the reactions 1.4 into 10 to the power of -4. Mechanism. Wilkinson catalyst, catalytic hydrogenation of olefins or acetylenes involving in the catalyst shown by the following mechanisms. Wilkinson catalyst on reactions with ethylene adds a molecule of hydrogen oxidatively to form a 16 electron 5 coordinated dihydro complex. This in turn adds a molecule of olefin forming a 6 coordinate 18 electron species. Transfers of a hydrogen atom to the beta carbon to yields a 5 coordinate alkyl intermediate, which then undergoes another rearrangement to give the hydrogenated product and to reform the bis-triphenyl phosphine rhodium chloride species is formed. These are the mechanisms. Then applications. Wilkinson catalyst is widely used for the hydrogenation reactions of unsaturated hydrocarbons. It can be used in the additions of a hydrogen acyl group to the alkenes. Then next one, hydroacylations of alkenes. The catalytic is highly effective in the selective reductions of the least hindered olefins. And next topic is lithium aluminum hydride. Lithium aluminum hydride is reducing agent in many organic synthesis. These are the content of lithium aluminum hydride. First one, structures of lithium aluminum hydride. Next one, preparation and properties and mechanism of lithium aluminum hydride. And last one, applications of lithium aluminum hydride in many organic synthesis. Lithium aluminum hydride, also abbreviated as LAH, is a reducing agent. It is used in organic synthesis. It is a nucleophilic reducing agent used to reduce polar multiple bonds like carbonyl groups. Lithium aluminum hydride reagent can reduce aldehydes to primary alcohols, ketones to secondary alcohols, carboxylic acid and esters to primary alcohols, amides and nitrates to amines, epoxide to alcohols, and last one, lactones to diols. Lithium aluminum hydride cannot reduce its isolated non-polar multiple bonds like C double bond C. However, the double bond or triple bonds in conjugation with polar multiple bond can be produced. Lithium aluminum hydride powerful reducing agent compared to sodium borohydride. Aluminum hydride bond is weaker, less stable than boron hydrogen bond. These are the structures of lithium aluminum hydride. Aluminum hydride ion hydrogen are arranged in a tetrahedral arrangement around Al3 plus ions. The coordination of hydrogen ion to aluminium 3 plus ion result in formation of lithium plus centers are surrounded by 5 AlH4 minus tetrahedra in the structure. A bipyramid arrangement is formed by the lithium plus centers being bonded to one hydrogen atom from each of the surrounding tetrahedra. Preparation. First one, lithium hydride, it's treated with aluminum chloride. Finally, we get the product of lithium aluminum hydride and 3 mole of lithium chloride. And another one, preparation, sodium, it's treated with aluminum in the presence of lithium chloride, and finally we get the product of sodium aluminum hydride. It's a reducing agent. Sodium aluminum hydride is also treated with lithium chloride, and finally we get the product of lithium aluminum hydride. Aluminum hydride, it's also treated with lithium chloride, and last the product of lithium aluminum hydride is formed. Next one, properties. Lithium aluminum hydride molar mass 37.95 gram per mole. It's a density of 917 kilogram meter cube. It's a melting point 150 degrees centigrade, boiling point 184 degrees centigrade. Lithium aluminum hydride is a white solid. Commercial samples are usually grey due to impurities. Lithium aluminum hydride, it reacts with 4 mole of water. We get the product of lithium hydroxide and aluminum hydroxide, and hydrogen it will be formed. The reduction reactions with the lithium aluminum hydride as the reducing agent must be carried out in anhydrous non-protic solvents such as diethyl ether and tetrahydrofuran. It has a high solubility in diethyl ether. Lithium aluminum hydride reduces carbonyl compounds to alcohols. Aldehyde is treated with lithium aluminum hydride. We get hydrated lithium aluminum hydride ion is formed, and 3 mole of aldehyde is treated, and 4 times of hydroxyl group is present. We get primary alcohol is formed. Lithium aluminum hydride reduces carbonyl compounds to alcohol. Aldehyde is treated with lithium aluminum hydride. We get lithium ions present. We added 3 mole of aldehyde. Its addition product of primary alcohol is formed. The reductions of a carbonyl group by lithium aluminum hydride is initiated by the attack of nucleophilic hydride ion on the carbonyl carbon to give a tetrahedral intermediate. Lithium aluminum hydride is a nucleophilic reducing agent. Since the hydride transfer to the carbonyl carbon, it occurs prior to the coordination to the carbonyl oxygen. It reacts faster with the electron deficient carbonyl groups. The reactivity of carbonyl compounds with this reagent follow the order. Aldehyde is greater than ketone as well as greater than ester, and greater than amide is greater than carboxylic acids. lithium aluminum hydride and reacts with a ketone. It's during the reactions. Lithium aluminum hydride is added across the C double bond O bond gives our aluminum salt of alcohol is formed. Further reactions with the ketone, one hydrogen attached to aluminum is replaced by carbonyl. Further reactions with another molecule of ketone, hydrogen attached to aluminum is replaced by a hydrogen. Thus, 1 mole of lithium aluminum hydride can reduce 4 mole of carbonyl compounds that on hydrolysis give free alcohol. These are the mechanism of lithium aluminum hydride. Next one, reactions. Aldehydes are reduced to primary alcohols. Aldehyde treated with lithium aluminum hydride, we get the product of primary alcohol is formed. Then another one, ketones are reduced to secondary alcohols. Ketone, it's react with lithium aluminum hydride, we get the product of secondary alcohol. And also carboxylic acids are reduced to primary alcohol. Cinnamic acid is treated with lithium aluminum hydride, we get the product of primary alcohols. Applications. Applications of lithium aluminum hydride. Lithium aluminum hydride reduces aldehydes or ketones to the corresponding primary or secondary alcohols. Acetaldehyde, for examples, it's reduced to ethyl alcohol, while acetone is reduced to isopropyl alcohol. Lithium aluminum hydride reductions of carbonyl compounds. Acetaldehydes is reduced with lithium aluminum hydride, we get a primary alcohol. And also ketone, it's also reduced with lithium aluminum hydride to form the primary alcohols. Lithium aluminum hydride is used to reduce carboxylic acids, esters and acid halides to their corresponding primary alcohols. For examples, lithium aluminum hydride reductions of acetic acid, methyl acetate and acetyl chloride to yield the same ethyl alcohol. These are the reactions of ethyl alcohol. Acetic acid is reduced with 3 equivalent lithium aluminum hydride in the presence of hydronium ion. Finally, we get the product of ethyl alcohol. And methyl acetate, it is also treated with lithium aluminum hydride, we get the product of ethyl alcohol. And last one, acetyl chloride, it's also treated with lithium aluminum hydride, we get the product of same ethyl alcohol is formed. Lithium aluminum hydride reduces the amides to amines. This method is particularly useful for obtaining secondary amines. Diethylamine, for examples, can be synthesized from acetyl chloride. Acetyl chloride react with diethylamine, we get ethyl acetate, and then lithium aluminum hydride is added, we get acetyl chloride is formed. Lithium aluminum hydride reduces the nitriles to primary amines. For examples, lithium aluminum hydride reduces acetonitride to ethylamine. Acetonitride is reduced with 2 equivalent mole of lithium aluminum hydride, we get the product of ethylamine is present. The next one, sodium borohydride. What is sodium borohydride? Sodium borohydride is an inorganic compound whose chemical formula is NaBH4 under normal conditions. This compound exits as a white powdery solid. Sodium borohydride is a reducing agent. It's widely used both industrially and organic laboratory scale. It can be noted that sodium borohydride is also known as sodium tetrahydroborate and sodium tetrahydroborate. Next one, preparation. Sodium borohydride can be prepared on an industrial scale by treating trimethyl borate with sodium borohydride at a temperature range of 25 degree to 27 degree centigrade. The balanced chemical equation for these reactions is given by 4 mole of sodium hydride, it's react with triacetyl borate, we get the product of sodium methoxy group and we get sodium borohydride is present. Alternatively, this compound can also prepared by reacting borax, metallic sodium, dihydrogen and silicon dioxide at a temperature of 700 degree centigrade. These reactions can be represented as follows. Borax is treated with 8 mole of hydrogen molecule and 16 mole of sodium that reacts with the silicon dioxide, and finally we get the product of sodium silicate, and the last final product of sodium borohydride is formed. These are the structures of sodium borohydride molecules. The salt consists of the sodium cation and the BH4 minus ion. It can be noted that BH4 minus ion is a tetrahedral structure. Boron is a central metal atom. These are the arrangement of hydrogen in tetrahedral shape. Sodium borohydride has 3 stable polymorphs, namely alpha, beta and gamma polymorphs. Properties. Physical properties of sodium borohydride. The molar mass of sodium borohydride is 37.83 grams per mole. This compound does not have any characteristic odor. The density of sodium borohydride at the standard temperature and pressure corresponds to 1.07 grams per cubic centimeter. It has a melting point of 673 Kelvin. However, it tends to undergo decomposition at this temperature. Chemical properties. Chemical properties of sodium borohydride. Despite being soluble in most protic solvents, protic means like living water, this compound slowly reacts with protic solvents, resulting in the formation of high hydrogen. Sodium borohydride generally undergoes decomposition in acidic and aqueous media but not in basic media. This compound is a reducing agent and can reduce a wide spectrum of organic carbonyls. Sodium borohydride also releases hydrogen when exposed to many metal hydrolysis. Uses of sodium borohydride. The primary uses of sodium borohydride is in the preparations of sodium dithionate, which is a bleaching agent for wood pulp from sulfur dioxide. Aldehydes and ketones can be converted into the corresponding alcohols with the help of these compounds. Several antibiotics such as thiophenicol, dihydrostreptomycin and chloramphenicol are produced by employing sodium borohydride as a reducing agent. It can also be used to reduce toxicity in aged. Thank you.